for coming. I'm excited to announce our speakers today who will be talking about the IFE-STAR program. We have Professor Richard Sandberg from BYU, Dr. Arianna Gleason from SLAC/Stanford, and Dr. Jimmy Negus from CSU. So they're here to talk to us today. So I'll hand it off to you guys.
Great. Thank you so much for being here. We kind of asked, how many of you are about majors and emphasis and disciplines? So we got mechanical engineers. Any other engineers? Any other engineers? Electrical? What? Okay. Any physics? Physics? Yeah, physics. Great. Do we have any other disciplines represented? Shout it out. Yes.
Chemistry.
Chemistry, yes.
Yay.
Any materials? Oh,
I was going to say high school.
high school, yeah. Okay. How many of you are undergrads? What about graduate students? Any graduate students? Yes, graduate students. Okay. And older people, faculty, staff. Okay. Excellent. All right, great. So I spent 10 years at Los Alamos National Laboratory, and I'm at Brigham Young University, but together with Dr. Gleason and Dr. Negus, we're actually not representing our home institutions here, but we're representing a national institute called the IFE-STAR program. So we're going to talk to you about that and why we're really excited about inertial fusion energy and why there's kind of a renaissance in fusion energy going around the world, okay? So we're going to split this talk into 3 parts, but really the goal here is we're connecting with universities, national labs, and companies. And so the fusion industry is workforce limited. We've got a lot of competition for brains like you, okay? We've got competition from AI, ML, data science, of course. We also have a lot of competition, specifically probably for your engineering background with lithography. The CHIPS Act is trying to bring computer chip manufacturing back to the United States. So there is a huge limit for people in STEM to work in this area. So that's one of the reasons why we're here talking to you. Okay, so this is the inaugural year of what's called Inertial Fusion Energy, or IFE-50. We're trying to get coast-to-coast representation and buy-in from people around the country into inertial fusion energy. So that's the story we're going to be telling. Okay, but I want to start with this story. So this is a report from the kind of famous consulting company, McKinsey. They're a financial consulting company, work with a lot of Fortune 500 companies. You may have heard of them. And this is a chart showing demand for electrical energy worldwide, okay? And it's in thousands of terawatt hours, which I guess is a petawatt hour for those of you who are keeping track. And this was a 2023 report. So it's a little bit old, but there was growth over about the last 25 years or so of 3% growth in energy demand worldwide. And their prediction is that it will increase to 3.5% growth in the next 25 years. Now you might say, who cares? That's half a percentage point. But if you look at the total demand in 2023, there were about 25 terawatt hours. They predict that by 2050, we could be as high as 64 terawatt hours. That's more than double, okay? That's a huge change. And this is a little bit old. It's a couple years old before some of the huge AI companies came out. But let's just dig into this a little bit. Some of the major growth areas is, of course, building, but it's not doubling in size, or industry, that's not doubling in size. What's doubling or tripling or growing exponentially is data centers, that's AI. And this number is probably way low. You probably know that every time you do a ChatGPT search, that's about 10 times more electrical energy than doing a simple Google search. But now when you do a Google search, you're using AI anyways, right? So that's a huge demand. The other one is electrical vehicles, transport. Every time you take a car off gasoline and you plug it in at home, that energy is still coming from it someplace, and it's coming from the electrical grid. So the Department of Energy, their strategy is all of the above, right? They are for traditional energy sources like coal and oil, also for oil, for alternatives, but fusion is what we're here to talk to you about today. Okay, and I'm not an energy expert, but I predict we're going to need to use every possible energy source we can to keep up with this demand, because AI is a huge, huge energy user, okay? And we all seem to want to use more AI all the time. Okay, so that's kind of the motivation. So we're going to break this talk into 3 parts. I'm going to start out first, and I'm going to talk to you about what is inertial fusion energy and why is it important. Then Dr. Arianna Gleason is going to talk about IFE-50. Every state has a role to play. And then Dr. Jimmy Negus will talk about IFE-STAR, opportunities for engagement today and in the near future for you and South Dakota schools' minds. Okay? So, what does IFE-STAR stand for? Oh, I pushed the wrong button, Jimmy.
Uh-oh.
We'll see. Okay. What does IFE-STAR stand for? It stands for Inertial Fusion Energy Science and Technology Accelerated Research. Okay? So that's what the IFE-STAR program stands for. So we already have inertial fusion energy power plant. It's called the sun. It's actually more gravitational energy. But it's been working for billions of years, thank heavens, because that's where we get all of our energy. That's where we get all of our food. It all comes from the sun originally. So what does the sun do? Well, it does proton-proton fusion. So it has a huge amount of mass in it. It's gravitationally confined. And it takes protons and combines them through this chain of events, producing neutrinos and positrons, and those actually help in the fusion process. Sorry, sit on somebody's lap. No, just kidding. There's a chair out here in the hallway you can pull in, or we don't mind if you just sit right here, I think. Professor Dick is getting more things. So we got neutrinos, we got gamma rays, but this all causes heat, all right? And every second, the sun converts 500 trillion metric tons of hydrogen to helium using the fusion process. So it is doable. It's been going on. It's the main energy source in the universe. So what we tend to do here on Earth, either through tokamaks, which may be a fusion source you've heard a little bit more about, magnetically confined, or recent success in inertial confinement fusion, is we do deuterium-tritium fusion. So these are both isotopes of hydrogen. So we have deuterium, which is what is in heavy water. It's got one proton and one neutron, and then tritium, which doesn't exist naturally because it has a short half-life, at least not in abundant sources. But the primary source for this kind of fusion is seawater. There is an abundant amount of heavy water in seawater, and we can pull that out. What was it, a tablespoon of deuterium could run in San Francisco for how long?
24 hours.
For 24 hours, okay? And that's a lot of energy if you haven't been to San Francisco. And so the process, you have to get these very hot, you have to combine them, and then it produces an alpha particle, which is just a helium nucleus, a high energy neutron, and a lot of energy. And so if you look at this, the little bit of nuclear fusion, the reason why this works is because these products actually weigh a little less, or a little more, or reactants. Oh, these are reactants, these are products, these are reactants. I'm not a chemist. Tell me I'm not a chemist, okay? So the ingredients, that's the word I use, the ingredients weigh more than the products, and the difference is the binding energy. So the binding energy is what we're getting back out when we bind these two together, okay? And that's through Einstein's famous equation, E equals mc squared. And so this is a metric that we probably should, our program manager loves, the Big Mac metric, okay? So we're thinking about energy. A Big Mac from McDonald's, see, there's the trademark, has 10 joules per gram of energy. All right, not that much, but there it is. Gasoline has 5,000 joules per gram. And DT fuel has, I forgot the number of zeros here, but that's 34 billion Big Macs equivalent of energy, okay, where gasoline is only 500. So that's a huge increase in energy. This would be the most energy-dense form of fuel that we have here on the Earth. So we should take advantage of it. So we already have inertial confinement. Oh, and why is this hard? Why do we have to get things really hot here? Because there's a cooling repulsion, right? These are positively charged particles, positively charged nuclei. They don't want to be close to each other. But when they get close enough, the strong force will kick in, the nuclear strong force, and they will bind and give up that energy. Okay? So these are the primary forms of fusion energy that are being pursued. We have, of course, gravitational confinement. The density is 10,000 times solid density where the sun is performing fusion. So very, very dense. Temperature is about 1 keV. I should add up here the temperature. I think that's about a million degrees, if I remember. Somebody, million degrees Celsius, okay? And the confinement time, which is just how long it takes for, you know, an electron or something to get out of the sun, is 100,000 years. Magnetic confinement is what's been pursued for many decades now. You might have heard of ITER in France. It's an international consortium developing a ginormous tokamak. This is basically a magnetic bottle where you want to heat up these deuterium and tritium ions in a low density gas and get them to combine. The density is lower density than solid by quite a bit, and the temperature is at 10 keV, which is, I think, about 50 million degrees Celsius. Okay, confinement time is seconds, meaning you're not confining the plasma for that long, it's going to escape. And so there's a lot of concern about damage here. The main problem right now is just these plasma instabilities are very hard to deal with. You've got to contain this hot plasma with magnetic fields. Richard Feynman, the famous physicist, once said, trying to confine a plasma with magnetic fields is like confining jello with rubber bands. It's doable, but it's hard, and you have to have a lot of rubber bands, okay? And so what we're going to talk about today is inertial confinement fusion. We're going to focus on laser inertial confinement fusion, but there are other people who are working on pulse power confinement of inertial confinement. So inertial confinement, we're going to go much higher density than solids, about 10,000 times the density of solids. We're going to, again, get up to like 50 million degrees, and we're going to have confinement times of only tens of picoseconds. So the way this is going to work is we're going to have lasers or pulse power energy magnetic fields crushing some pellet of fuel, and we're going to smash it inward, and it's basically the inertia of that implosion process which is going to confine it only for a really short time. Sorry, wrong button here. For a really short time, but that confinement is going to be so dense and so hot that it'll give time for those nuclei to combine and burn the rest of the plasma. All right? And if you have questions, shout them out. If they're too frequent or too long, we'll just start ignoring you. Okay? But a few random questions, we're okay. Okay, so the first time we as a species performed inertial confinement fusion where we got more energy out than we put in is at the National Ignition Facility in Lawrence Livermore, California. And this was, that's Ari's representing here. And so this is the size of the National Ignition Facility. Here's a truck. It's 3 football fields in size. These are, you know,
we were sad to
Bay
see
Area,
the
yeah, Bay Area or formerly Bay Area. This should say Las Vegas
Las
for those of you
Vegas.
who are keeping track. Bay Area football teams, okay. So how does the NIF work? That's the more important thing. Let's see here. We're going to watch this YouTube video, which is just a couple minutes.
The universe, for billions of years, has been lit by the fire of countless stars. In these stellar cauldrons, hydrogen nuclei are fused together to form helium nuclei, releasing energy that lights the heavens. Can we build the technology to harness this awesome energy on Earth? As we approach our planet, that is exactly what's happening today. Far beneath these clouds lies the National Ignition Facility, located at Lawrence Livermore National Laboratory in Livermore, California. This facility has been built to bring star power to Earth. It is the world's largest and highest energy laser system. Containing 192 laser beams, NIF will explore controlled nuclear fusion to ensure global security, enable sustainable clean energy, and advance our understanding of the universe. 85 feet tall, the laser and target area building is the size of 3 football fields. Inside are 2 parallel laser bays, each containing 96 beam lines. In this animation, which is millions of times slower than real time, we will follow the process for creating a miniature star in the target chamber by riding along with some of the laser beams. The process starts by first energizing the laser amplifiers in the 2 laser bays by dumping electrical energy stored in capacitors into flash lamps. They convert the energy to light that is absorbed by the laser glass in the amplifiers. Later, when the laser pulses pass through the glass, they will extract this energy, thereby increasing the laser beam energy. Our trip with the laser beams begins in the master oscillator room, where a very low energy laser pulse is created. This pulse is only 20 billionths of a second long in duration, which is a beam of light about 20 feet long. It's amplified and then split into 48 laser pulses, which are carried over to the two laser bays using fiber optic cables. Here, the 48 pulses are amplified in a preamplifier by a factor of about 10 billion. Then they're split into 192 pulses and sent into the main laser system. As we track 8 of these beams through the facility, you can see the path of the beams highlighted in red. The first amplification occurs in the power amplifier. It has 5 glass slabs that were energized by the powerful flash lamps. Then they travel to the main laser cavity that directs the laser light back and forth 4 times through 11 sets of laser amplifier glass in the main amplifier system. This gives the laser beams another boost of energy. During this time, optical components ensure that the beams maintain their required pulse shape, quality, and spatial uniformity. On the final pass through the optical system, the laser light is allowed to exit and travel back through the beam lines and up to the power amplifier once more to pick up even more energy before heading down the long stretch to the switch yard. In total, the energy of the laser beams is increased a quadrillion times as they travel more than 1,500 meters from the master oscillator room to the target chamber. In the switch yard, the parallel bundles of beams are rearranged into a conical configuration. That's so they can be focused into the center of the target chamber and onto the target assembly. The assembly holds the spherical fuel pellet containing hydrogen. Here you see the 8 beams split into 2 groups of 4 beams each, one group traveling up and the other traveling down, heading for equidistant entry ports on the target chamber. Finally, the beams pass through the final optics assemblies, which convert the original infrared laser light to ultraviolet.
Okay, that was all laser physics. Now is the really cool part.
Yeah.
The beams then converge on the 10mm target assembly called a hole run, generating a path of X-rays. This causes the tiny target sphere to implode and ignite in a controlled, self-sustaining fusion reaction. The same process that powers the stars. This will be the start of a new journey that will bring not only discovery and innovation, but a lasting legacy to the future.
Okay, so that seems like a lot of lasers stuff, but it really, this was first, okay, so they've been doing this, NIF turned on in like the early 2000s, right? But what's really exciting is a few years ago, on the 5th of December, we were calling this shot heard around the world. The NIF was able to get more energy out in fusion energy than they put in with the lasers. So that's called scientific break-even. And that's the first time as a species we've obtained a burning plasma, burning fusion plasma in a controlled manner. We've been doing that since 1952 with thermonuclear weapons, but most of us don't want to see those ever used again, right? But now we can do that in a controlled manner. And it really has set off a worldwide race. So since NIF did that in 2020, they can shoot maybe once a day. This is 1990s laser technology. Okay, there's much better laser technology now. But since then, they've done this where they've gotten more energy out than they put in 8 times. And recently, this year, they were able to get 4 times more energy out than they put in with the lasers. Now, that's a long way from engineering break-even, where they're getting more energy out of the fusion than they put in from the electrical grid, but we're making great gains. And you might be like, well, they've only done it 8 times in 3 years, but they're doing a lot of other tests there too, right? So they don't get to do only these kind of inertial fusion energy shots. And some of the shots they've done have been to see why it doesn't work, okay? But recently, the United States, the United Kingdom, Germany, the European Union, Japan, China, and South Korea have all moved up their target dates, not for fusion, just scientific breakthrough, but for a fusion power plant, where they actually could put energy back on the grid. Some of them had it in the 2050s or whatever. They've all moved it up to the mid-2030s, so within the next decade. Will we get there or not? That's for us to decide as science and engineers. but we're quite excited about this. So just briefly, the fusion triple product is what you need to achieve fusion energy. So you need fusion density or fuel density, we're going to call that N. You need a lot of collisions per unit time, and so that's kind of like the fuel density, right? We have to gather the fuel together if we're going to use this campfire analogy. We have the temperature. We have to have some kind of heat to ignite the fuel, okay? So that's the fuel temperature. And then we have the confinement time, which is plasma needs to hang on to fusion heat to make more fusion happen. So that's not too different from our campfire. We can have heat to start it, but if we immediately distribute all that fuel and spread it apart, we're not going to have enough confinement time of the campfire to ignite the rest of the fuel. Okay, so that's this third part. So the primary aim of nuclear fusion research is to maximize this triple product. That's what it's known to the community. And why are we so excited? Well, this plot is a little complicated, so let me talk you through it. But this is years. I think you got years. That makes sense. And this is the triple product, okay? Right here is density, temperature, time in 2 different units. This is for inertial fusion energy, and this is for tokamaks. And on here, we have all the different types of fusion technology which are being pursued. Tokamaks is magnetic confinement, Accelerator is a magnetic confinement. And you see a lot of points are going up there, getting closer and closer to break even here. But this line right here is break even, and the only plots that have gotten up here and actually achieved this is NIF, the ones that have gotten over scientific break even or achieved a burning plasma. And so these SPARC and ITER, these are projected. And ITER recently moved out their projected date to start doing fusion experiments by another 10 years. Okay, so they're going the wrong direction, unfortunately. Okay, so inertial confinement fusion is the only method that has achieved a burning plasma, hence a lot of hope for IFE or inertial fusion energy. So I'm going to stop right there and turn it over to my colleague, Dr. Gleason, who's going to talk a little bit more about this program.
Great. Thank you so much, Professor Sandberg and Dr. Negus. I'm really excited to be with you here today. First, I want to start, look to your left, look to your right. These are the future scientists and engineers, right, that may help us carry this concept forward to providing an alternative, reliable, domestic energy source for the United States. And part of what I want to share with you is how we get to doing the job done, the actual technical challenges that we together can face through science, engineering, technical workers. You don't need to have a PhD, right, in order to make a difference in this community. And so I'm really excited to be here today. I'm a senior scientist at the SLAC National Accelerator Laboratory, adjunct faculty at Stanford University, and delighted to share with you where we are today in inertial fusion. So, whoops, going the wrong way. So the pave stones that will take us from the science, the discovery that was made at the National Ignition Facility, really a drop the mic moment, right? Shot heard around the world. That was the first time, right? I had friends and colleagues, they had pagers, maybe that's a little too 1980s, but they had, announcements go out on their phone, and it was a really exciting, thrilling moment. And it took decades of effort from scientists and engineers to get that to be possible. But taking that physics experiment, right? It's a physics experiment, and the leap to an energy solution for the United States that is resilient and domestic is going to take a lot of effort in many different categories. And so what I want to share with you is that many of us in the science community have come together and tried to identify what are those technologies that need to be advanced, right, for commercial fusion energy to be in a 5-year time frame, right? And part of what we're able to do is bring together private industry, which, by the way, $12 billion to date has been invested in private company startups between magnetic confinement and inertial confinement, right? Let's partner with private industry in academia and at the DOE, Department of Energy National Laboratory Ecosystem to de-risk those critical technologies. And so many of the challenges are listed here, and we're going to walk through these one by one, but sort of a cartoon concept of what we're trying to do. redevelop design for higher rep rate, right? Professor Sandberg mentioned the NIF can only fire once per day, once per 12 or 24 hours. But in order to make this energy efficient, we need to be shooting these fuel capsules in a fraction of a second every second. So maybe 10 hertz, right? So 10 times per second. And we have to deliver those fuel capsules at that rate. We need to track those capsules, right? And engage the laser or your confinement driver in that fraction of a time. We need to then breed the tritium, right? Remember, Professor Sandberg said the tritium only has a half-life, it's about 12 years, right? The Earth has we have a small inventory of tritium. In order to be self-sufficient, we need to breed that in using what's called a lithium blanket material, right? So we need to cultivate these raw materials in order to sustain that. The excess heat that is generated from this reaction then can heat water, turn turbines, deliver energy to the grid. So all of this needs to be set up, and there's a lot of work to do, but we are excited to meet that challenge. So one of the areas where technology is really taking off, we saw in that video so it was sort of a 1990s style video, right? Okay, sorry, we need to upgrade that. But the laser technology is what's called flash lamp technology, but we need to update that to diodes, right? And there needs to be investment in this kind of technology for more efficiency. We need to understand what kinds of materials, the optics components, the glass, right? Remember it mentioned like, oh, these large scale foot by foot sized glass panels that are used to direct the laser, that all had to be developed. An entire industry was stood up just to deliver those glass components to the NIF, right? We need coatings. I mean, for heaven's sake, if you're sending kilojoules of energy routinely through glass, you sure as hell better have high quality coatings, because otherwise you're exchanging glass every day. We can't do that, right? So developing key technologies at the nanoscale, right? Engineering materials in a way that is beneficial, right? And then having a component of theory and simulation to ensure predictive capability. This is clearly needed just on the laser technology side, right? But Professor Sandberg also mentioned there are other kinds of confinement approaches. One is called a Z-pinch, where basically you have magnets that are separated, held apart. The force on those magnets can sometimes reach the same force that it would take to stop a 737 as it decelerates on the runway. That is a lot of force, right? And so that sort of force, once you release and bring those magnets together, can also confine your or orchestrate that confinement fusion process. So there's a lot of work to do before we get to electrical break even, and part of that is upping our game on laser technology. Okay, the fuel capsules. Okay, this is where my heart is. I do a lot of work with Professor Sandberg and others at some of the Department of Energy national laboratories and other academic institutions to figure out, how do we hold our fuel, right? Well, we can't just like pop it in like we do with gasoline into our car. We have to actually take the deuterium and the tritium. First of all, we have to extract the deuterium from that tablespoon of seawater. Okay, but that's an abundant starting source for the deuterium. We need to then hold that fuel capsule together somehow. So lots of engineering nanoscale features needs to be pursued. There are opportunities in chemistry, in the nanosciences, in how these fuel capsules are constructed, because now I just told you we have to operate at like 10 hertz, right? Which means I need enough fuel capsules holding that DT in the billions at a cost that is about 3 pennies per fuel capsule, right? 3 pennies. Now the NIF, when it went off, right, heard around the world, that was a $3 million, okay, I should say, because that's taxpayer dollars, right? Okay, but look, it was a very expensive fuel capsule, but we need to change the paradigm, right? We need an inexpensive approach for mass manufacturing these capsules. Now, is this the right approach? A lot of the work I do is on nanofoams, different kinds of polymerization methods. We can borrow from the photolithography industry, right? The chip manufacturers, they do a lot of work with resists and leveraging EUV to harden different kinds of polymers. So we can borrow technology. Is that the right solution? You know what? Actually, we don't know, right? We have a lot of good ideas, a lot of good opportunities for research, but we need you guys, right? We need folks from every state in this country to be joining this call to action so that we don't lose our leadership in fusion. Right now, we are there. We have it. The NIF was successful. It's the most powerful laser on Earth, right? But we got a lot of great competition now. So it is up to us to cultivate that future workforce. And that's another reason why we call these out. Okay, tracking and engagement. Here's another exciting, keeping track of the time, another exciting opportunity in target delivery. So I said, okay, we have to operate at 10 hertz. I need a lot of capsules. And now I need to launch, thank you, I need to launch that capsule and track it. It turns out that in order to meet that rep rate, I need to be executing a target, a capsule that's moving at about 100 meters per second. And then I need an adaptive mirror, some sort of final optic to engage that capsule, right? All of that is hard. And we've got some starting place technologies that different universities, UC San Diego, other colleagues, University of Chicago, there are a lot of different institutions that are pursuing target tracking, leveraging AI/ML, so that we get real-time feedback and predictive capability for where to steer that final optic. But they're all toy models. In other words, these are all just at a laboratory scale, sort of the size of one of these desks, right? Where we need to go for commercial fusion energy is scaling, right? And thinking about what do these private companies need at scale. What does the final chamber of this commercial fusion plant, it's going to be 10 meters in diameter, right? 10 meters in diameter. And I have to track this pellet. It's about the size of a peppercorn, right? And I need to know exactly where he is to within 25 microns, right? That's hard to do. Or is it, right? I think there are a lot of fantastic ideas out there. So part of my work at SLAC is actually setting up one of the first test stands for doing real-time target tracking at scale. So again, what Dr. Negus will talk about are ways for you to engage. If you want to come and shoot pellets at 100 meters per second with me at SLAC, you are more than welcome, and we can figure out how to get you engaged. Okay, so coming back to sort of the holistic view, right? We've just talked about a few of the different technologies needs, but there's a piece here that I want to call out specifically in South Dakota. You have a rich resource in lithium mining. And I know that that might come with a lot of strings attached, but it is to say you have this natural resource. This community, the fusion community, is interested in partnering with what you're already doing, not expanding a footprint in mining per se, but to upcycle. Not just recycle, but upcycle where the different companies are in terms of lithium extraction and separating different isotopes of lithium that might be strategic to the fusion community. We need that lithium for breeding tritium, right? And tritium is critical in the fuel cycle. And so all of these pieces, then materials, another thing close to my heart. I'm a geologist by training. So thinking about materials at extreme conditions, I studied planetary interiors for a long time. And so thinking about steels, iron, how do we manufacture more robust, resilient steels? They have to maintain such extraordinary forces in these fusion reactors. And so we've come a long way, but there's still a lot of problems in thinking about how to tailor at the atomic level. You know, some of the experiments that we do and that the IFE-Ecosystem partners do, we are able to track at the atomic level. We ride along with the atoms, right, using these fantastic X-ray light sources to realize how these materials are behaving under extreme conditions. That improves our predictive capability, right? We are at the appropriate length and time scales, angstroms and femtoseconds. that match the codes, the models that are being used even here in your department. So there's a lot of opportunity. We are looking forward to keeping the lead here in the US. But like Professor Sandberg acknowledged, there's a lot of funding from other governments that are like-minded nations, and also not so like-minded nations that are looking at fusion and the rich opportunity both in the energy space and in the national security space. And make no mistake, folks, it is a race, right? And whoever gets to commercial fusion energy first will change global economics. Okay, drop the mic. So we need to be aggressive and attentive and participate in opportunities in this community. So this is just to say that our government is trying to support this work. There are opportunities in public and private partnerships. So that means your tax dollars, right? Getting partnered with private industry, that $12 billion, to advance the critical sciences and technologies for fusion. And the actual immediate steps you can take are going to be shared by Dr. Negus. So what will it take, right? I want you to see yourself here in these many different job opportunities, right? And it doesn't take a PhD. I've given talks at other community colleges, high schools, even elementary schools, my kids' schools, right? To show that you can be a scientist, you can be a technician and make an incredible difference, right? Again, when I said look to your left, look to your right, we are in this together. We are all here on this planet using energy, using ChatGPT, using Google, and opportunities for delivering reliable domestic energy is really at our doorstep. And so I hope you can find yourself in this future. But the actual next steps of how to get engaged will be delivered through Dr. Negus. And just to say, we have a strategy of reaching out to every state across the United States. And so this is our maiden voyage. You guys are our first ones. And we are moving all across the US and wanting to build these partnerships. And how to do that, I will hand it over to my colleague. Awesome. Thank you.
Thank you, Dr. Ari and Dr. Sandberg. My name is Dr. Jimmy Negus, and so my background is actually astrophysics. There's a dark matter guy here, right? Awesome. So it's to show you, right, geologist in training, astronomer in training, you don't need to have a single discipline as your training in order to be a participant in fusion energy. So I'm here to show you the actual opportunities available to you guys as students and potentially to mentors. So this is the IFE Summer Undergraduate Research Experience. Last year was our first ever IFE-STAR year. It's run during the summer. Last year we had 120 applicants and we had about 50 paid positions at roughly 12 institutions. And so these are universities, national labs, and companies for private industry. And of course, the fusion industry is a workforce limited one. And so IFE is an excellent attractor of talent. And here you can show literally all across the continental US, there are hubs related to fusion energy. And last week, someone from the University of Hawaii contacted me about getting involved. So there might be an opportunity off in Hawaii as well. So IFE-STAR. So it's an opportunity to do IFE summer research at partnering organizations and universities, which include the University of Rochester, Colorado State University, Marvel Fusion, Exeter Energy, Lawrence Livermore National Lab, SLAC, BYU. Still waiting on those applications. And then, of course, national professional development workshops and seminars. So a big part of this program is we don't just want to have you do research and not equip you with the tools to be successful throughout your careers. So part of this professional development is, how do I deliver effective presentations? How do I actually write a research paper? We want a holistic approach for that training as a career scientist or an engineer, or even as an outreach coordinator. And at the end of the summer, we do have a fully funded student symposium in Washington, D.C. And so this past summer, Richard was there. You had a chance, the students, to go to Washington, D.C. and actually meet with congressional staffers as well. And so from the Department of Energy to fusion energy partnerships, you can actually see behind the scenes how this funding is prioritized and ultimately disseminated. And so here are some images of students in the lab. So these students are from CSU, which is not very far from here. And then here's our poster. So I'll have a link on the final slide, but applications are going to open October 9th and they'll close January 14th. And this year is going to be way more competitive because we want more students involved. So I would definitely, if you have any questions, you can reach out to me. And you can also take a look at the current institutions up now to get a sense of what research would be cool. Okay, and there's also the IFE-STAR conference. So this year we got very lucky and we were actually at Breckenridge, Colorado. So that was actually the first week I started, very beautiful location. And this conference, right, it's an annual opportunity to showcase recent developments in IFE. And I think during this conference, we actually had one of the shots announced for a big target gain. And so this field is very dynamic and updates are continual. It's also an opportunity to build community. So networking, right, as undergrads or graduate students. I just graduated grad school 2 years ago. The power of networking, right? Sometimes one single contact can be a breakthrough into a certain position. And so the IFE-STAR meeting is one of those opportunities to network with industry, national labs, and university individuals. There's also an interactive poster session. And this year, actually, we had about 200 participants. So 50 students from universities, national labs, and private industry. We also may have travel grants available. So if you want to go and you don't have funding or your mentor doesn't have funding, we might be able to help you out and get you there. And this year is going to be in Washington, D.C. Okay, so here, if you want to follow us, IFE-STAR.org is here. We also have a YouTube channel and a LinkedIn site. So I try to
pull out those phones. This is the time to pull out the phones. Right?
So LinkedIn is probably the most direct way to get updated. I try to update that at least once a week. And then our YouTube channels are growing. So we have one for the main ecosystem, as well as what's known as the RISE Hub, which CSU is a hub leader on. IFE-STAR will take you to the internship opportunity. So if you're on the main website, you can go to initiatives and then outreach and events, and you will find an application link to next year's IFE Sure Cycle. And our target audience is everyone, right? We're not looking for one type of student or mentor. We really want a cross-disciplinary cohort. And yes, so like they mentioned, fusion energy is a race. Let's win. Here is our graph that Dr. Sandberg introduced. The target gain continues to grow as we learn to harness the capabilities of our laser drivers, our coatings, and really getting a better, more strong workforce that's capable of conquering these challenges. And so IFE needs you to get involved, and we're happy to take questions. Thank you.
So maybe just two quick things. If there's anything you do right now and you want to stay connected, if you click on this QR code or scan this QR code, it'll take you to like a 2-minute interest survey. You can just fill that out, and then you'll be added to our emailing list, and you'll get a newsletter and some more information.
Absolutely.
And then 2, there's going to be a pizza lunch. Where's that going to be?
Pack Ballroom in the Kara Alumni Center.
Okay. So we'll
Right
be doing
after.
that right after this. It's targeted for students, but everybody can come if you want.
Yeah.
And
Come eat pizza. It'll be delicious.
Yeah. But questions?
Yeah.
What can you do if you're not in college yet?
So there's the Casper camp,
Yes. There's a Casper camp. If you click on that QR code or fill out that survey, we'll get you information. There is a summer camp. But I don't know what we'll do. If you're accepted to an undergraduate program starting next fall, I think you probably could apply for the IFE-STAR program, or the IFE-SURE, the summer
You could.
undergraduate program. And do that the year before.
Okay.
I would also say, oh yeah, go
Yeah, I'm
ahead.
just curious, what are your major funding agencies?
Department of Energy, Fusion Energy Sciences.
So within the Department of Energy, there are different programs, and we are funded by the Office of Science. Yeah. To follow up on non-undergrad opportunities, high school opportunities, there are also programs through SLAC, National Accelerator Laboratory. And so if you just get connected by this survey, we can route you that information as well. Yeah.
Yeah.
So you were talking about the tritium and the deuterium and how helium's a byproduct. I know some like traditional coal mining companies are trying to get into helium mining. Would that be like radioactive helium, or would we be able to reuse that helium?
So what's fantastic, but for them, but maybe not for us, right, is the helium actually causes embrittlement in some of the structural materials within the reactor. So it does effectively lodge itself. It can form helium bubbles, right? And so there could be a paradigm where it's a pain in the ass for us, right, for reactors, because it makes the steels or tungsten is also used as another main structural material in some of these concepts, because it embrittles them. It makes them not very strong, not very ductile, but it could be pivoted around that challenge and extracted. And so I think there is some cross-pollination that can happen there.
I'm not sure this would be the largest volume of helium you could get at, but
Yeah,
it might be.
it's definitely a big byproduct.
Just gonna ask.
We'll come back to you. Yep.
So are you able to speak more on the lithium mining in this area? As I know a lot of like where that's located here is in the Black Hills, and
Yeah.
what that would kind of look like.
So I've reached out to a few companies, and I think the message is that this is a new opportunity for them, and the quantities of lithium that we would need in a form factor that's either a solid or molten, what's called a molten salt. So you actually melt the lithium. Lithium will also then form hydride, or it'll do what it's going to do. But the opportunities to leverage what's already being extracted kind of in partnership or in a synergy with the mining and the volumes of material extracted naturally, the spodumene in the pegmatites and all this sort of thing. I think there's an opportunity to understand. We first need to understand the landscape and say, hey, we're a new community coming in. Here's a raw material that we need. How can we work within your current ecosystem so that we're delivering the kind of lithium we need for these reactors? Because it turns out there's another step, which is isotopic separation, lithium-6 and lithium-7, and we need 6. But maybe we could get that from the other EV or lithium energy utilities if they don't want it, right? And then we take it. So I think there's an opportunity to not increase that footprint and affect the local communities, rather take what's already going on and reuse it in this really new way.
Could I make a comment on that? And
Yeah.
so this is where inertial fusion energy is becoming a manufacturing engineering or
Yeah.
an industrial engineering problem.
Yeah.
Right? How do we do the separation of these isotopes? How do we do it? How do we extract it from old batteries, which are no longer being used, right? Because our huge competitor for lithium is going to be EVs and the batteries all of you have in your pocket. Do you want to tell them how much we need per power plant?
We need, the order of magnitude is 10 to 100 tons per reactor, right? Let's say it's 100 tons per reactor. And let's say we get, a reactor in, multiple areas in each region of the United States, right? So that's a lot of lithium. And I think right now the cost estimate is that for our community is that it would be cheaper for us to buy Teslas. Okay, wow. And then
At
pull
current
the batteries.
technology. At current technology.
It's current technology, right? To buy those Teslas and pull the lithium out of there, separate the lithium-6 and 7, and then use them in our power plant design. That doesn't sound very economic, right? So we need to go back to the drawing board and go to the source and utilize raw material supply chain buildup.
There was a question in the back, I think. Yeah.
Oh, yeah.
So the heater and the drawing,
fuzzy tungsten, yeah.
Are the same challenges there for the also the same structural challenges?
No, the structural materials are a bit different. So issues like the fuzzy tungsten, which is a big brain in the butt, right? This lithium, or excuse me, helium embrittlement and so forth, we do not face those same challenges because our walls will actually be this molten salt. Because on purpose, we want to breed the tritium. And so we don't need, graphite or lithium, graphite or tungsten walls. So there's still materials science's challenges, right? But they're a bit different. But in some ways, maybe on the steels, right? Manufacturing steels, building up the structural components that will actually be the framework for the reactor, that is still very much in common. Yeah, great question.
We'll go here first.
Can you
Go
briefly explain how you change infrared laser light into ultraviolet and then X-ray?
Yeah. So there are nonlinear crystals. Actually, some laser pointers that are green, if you move them very quick, you notice they make independent spots because it's actually a pulsed laser. So it's a second harmonic generation. So you start out with infrared, like 980 nanometer laser diodes, which is what your remote control for your TV has. Used to have, and then you go through a crystal which doubles that frequency, makes it green, and then another crystal which makes it ultraviolet. Then that hits that gold Hallraum can, and that's called indirect drive fusion, and you're converting the ultraviolet light into X-rays through a plasma. And so that's really inefficient for NIF, right? That's the best they had at the time. We didn't have time to mention this, but there's on the order of 50 private fusion companies in the US and Europe. And a lot of those companies are doing laser direct drive fusion, where they want to get rid of the Hallraum, get rid of converting to X-rays, and use short wavelength ultraviolet excimer lasers to directly compress the fusion. So that would be probably 10 or 100 times more efficient from the go. Question here?
How about for international students? Do you have the same opportunity for all countries, or?
For the IFE-STAR program, currently it's only U.S. students, but if you reach out to me, I can keep you posted. Yeah.
So there are programs at individual universities or I think
national
SLAC,
labs,
or national
right?
labs.
Office of Science Laboratories. Also, we welcome international students all the time.
Yeah.
So my home institution set up its own little RU program that's funded by the university, so we can get around that.
Yeah.
So if you fill out this survey, we can get in touch and let you know about these opportunities.
Yeah. I think there was one down here. And then
He had his hand up.
Oh.
He already got one question,
Oh,
so we'll
okay.
come back.
Could you tell me some about the cooperation between the private sector and the government side of things?
Yeah, there are a few existing opportunities where there's a cost share set up already. So, for instance, different technical challenges. Let's talk about maybe magnets or capsule design, right? So private companies and let's say a national lab, individual scientists work together and they write a proposal. And fraction of that money comes from our tax dollars, right? So it's public funds. But then there's a cost share up to 50% from the private industry. And what that does is over a period of 1 to 2 years, you work that technical problem with these TRL, so technical readiness level, you advance the technology up a few notches in those few years. And oftentimes it's encouraged to have students to have postdocs in early career. So that's one, the program itself is called Infuse. So that's one opportunity. There's also a recent, what's called Milestone program through the Department of Energy, where again, there is some, actually it's a much smaller fraction of public funds, but through a framework of experts sort of adjudicate these different private companies. Some of the companies, right, will be very successful, but the majority of them will not, right? Because some of the concepts will be just not efficient, or maybe the science isn't that good, right? But we're not here, the DOE isn't here to pick winners, right? People can apply to this Milestone program, and it's adjudicated by a large body of experts. And then there's that funding opportunity in this Milestone program. So there are a few more. I think there will be more coming down the road, opportunities to have public and private funds join together.
I'll just mention, we talked about those 3 hubs, one at
Yeah.
University of Rochester,
Oh,
one
right.
at Lawrence Livermore, and one at Colorado State. And each of those hubs are mostly academic and national lab research institutions,
Yeah,
but they're all paired with multiple private companies.
yeah, already.
And so we
Right.
already, as our hub, we meet with a company Exemer in Denver and Marble Fusion, which is another company in the US and Europe.
And General Atomics is another company that does a whole range of different things. It's a defense contractor, but it also does fusion and aerospace. And then there's a third opportunity called these FIRE collaboratives, but it's basically a fusion innovation research engine. And the point of that's where some of this target injection I was talking about. We are working with companies, private fusion companies who are like, hey, I need an injector, right? How do we work to de-risk those technologies? And so again, they sit on our advisory boards. So those companies can directly tell us scientist folks like, hey, you got to be working on this for me, right? So there's a good exchange of information and partnership there.
And one thing, as evidence of this collaboration, so Marble Fusion and CSU are building a $150 million facility right 6 hours away. So they are very much working collaboratively.
Close by. Yep.
Thank you so much.
Thank
If
you.
you've got to run to class or something,
Yes.
go ahead, but we'll stick around for questions.
Yeah.
And pizza over in the carrot.
Yes, sir.
As it might not be aware, in particle physics, we're dealing with natural fusion, for example, in rock all
Yes.
the time. So for us, that's unwanted background. So that it happens is not unusual. Also, for solar neutrinos, that were also discovered here, like this.
Right.
Absolutely.
So when I was going to school, that was next to a genetic column, and they were saying, oh, in the next 10 years, there will be a breakthrough. So now this was 25 years ago.
I know.
So Wendelstein 7 with Accelerator, they have their world record, if I recall, for the length in time of the confinement.
Mhm.
But you guys obviously have now the record with getting more energy out.
More energy.
In the triple
Exactly.
figure of merit, basically, of the triple product.
Yep.
So what makes you guys believe that you can upskill this and make this commercially viable compared to the other ideas that are out there?
The other concepts.
Can I
Yeah,
come up to
yeah,
that? So
please.
it is definitely a race, right?
Yeah.
And this is the Inertial Fusion Energy Program, so that's what we're representing. But Commonwealth Fusion is one of the biggest fusion energy companies, and they are building the first tokamak that's going to be at scale to produce power, most people would say, in outside Boston, Massachusetts. So a lot of people say Commonwealth is probably going to beat ITER. Right, so yeah, it is a competition, it is a race, and there's some amazing advances. I think Wendelstein 7's record was recently beaten by another place, I can't remember which one, but it is a race internationally. China announced that they're going to build a laser bigger than NIF. There's some discrepancy about, is it 10 times bigger, is it 2 times bigger, but that would allow them to do a whole lot more science, learn a lot more. They're keeping it kind of under wraps. But it is an international race.
And having the backing of the Department of Energy, right? It's not just a bunch of scientists scrambling. Like we have the investment from the Department of Energy.
When I see the budget for fusion is relatively small compared
Yes.
to the budget of DOE. So most what I saw on the charts here is private funding.
Yep.
That's right.
Vast
And-
majority. Yeah.
And that's what we're trying to leverage, right? And be connected in that way. I think another synergy though with high energy particle physics too is on some of the technologies for diagnosing, how far along can we get in this fusion process? So detectors, right? Ensuring that they're rad hard maybe, or can survive different conditions. That's another opportunity for building that synergy.
So you need those detectors to monitor basically the fusion reactions.
Yes,
and
100%.
poised in the reaction.
Yes, yes.
For like, if you're doing it at 10 hertz, you can't take the shot.
And
be
then,
like,
and then onboard compute. So it's one thing to just sense it, right? Have a sensor that's active and then reads the data out later. We need to have real-time AI/ML on board the chip, right? And so that's where the community is going, I think, also in many different communities. Yeah. Oh, we gotta go.
Yeah,
Oh, I'm sorry.
There's one quick question. is all,
Okay,
but-
yes.
So you say that a lot of different nations are projecting like a fusion power plant in the mid to late 2030s. But you're also talking about the dozens of different technologies that need to be developed, tested, and implemented. And then once that's all done, you need to combine them all and then design and build a fusion plant to be commercially. So do you think that is going to be commercial fusion in the 2030s, or do you think just any type of working fusion?
So the most are projecting a working power plant that will produce, I mean, they call them pilot plants, right? But a pilot power plant. And I was shocked by this, but a few years ago, and it'll be interesting what happens, a company called Helion Fusion out of Washington signed an agreement with Microsoft, right? The company we all love to hate, Microsoft. And they said they would be producing energy from Microsoft's data centers by 2028. So you might be like, that's impossible. But if you look at what we've done with the Manhattan Project or with the space race, I mean, when we get together as a group of people and put all of our abilities together, we can achieve things in shorter times than 10 years. So I don't know. That's what I'd say. And like it was pointed out, this is a small fraction of DOE's budgets they spend on nuclear bombs. So if countries in Europe are saying they're putting billion-dollar investments into fusion, the U.S. is behind on that.
Thank you guys so much. Let's thank our speakers from last time.